unsupervised learning. This is a huge field. I inevitably I'm going to be sort of, just have to focus in on a few things. So I'm going to make this distinction, which I'll explain in a moment, between sort of classical sort of unsupervised learning and what I'm going to call semi-supervised learning. And basically, I'll try and look at sort of the approaches that people think about in each of these areas. As the distinction isn't perhaps as it is a slightly artificial distinction, as I've explained, but I think it's helpful for just trying to organize what is really an absolutely enormous body of literature in this area. So, but before I get to any particular method, I think we just do some little bit of motivation around supervised learning. So, in practice, so if you take all these common data sets that I was referring to just in the last lecture, they have this sort of uniform distribution across the classes. What I mean is that every class has the same number of examples. Okay? Now, unfortunately, in the real world, that's just not how things work. So if you take, a big data set of objects in the real world, this is vision, this is words in Wikipedia, what you discover is there's this very, very skewed distribution. So you have a few classes that are very prevalent, and a huge tail where you have tons of classes which are just rare or incredibly rare. So this is just plotting, histograms of frequency on a sort of log scale here, so that it looks like a straight line. In practice, this thing would, of course, means it's telling you that there's a huge tail that goes out. So there's a bunch of words in Wikipedia which only occur, if this is log 2 or whatever, 10 times or something like that across the whole of Wikipedia. So there's no way you can get. There just aren't like a million examples of a particular word being used to train your deep net on. Okay, so in some sense we need some way of training which, you can't just rely on this purely supervised paradigm for really going to solve problems like this. And this sort of situation crops up, absolutely everywhere in the real world. Okay, so that's one sort of clear rationale behind it. You need to be able to do something, that leverages the structure of the data itself, not just these sort of manually provided labels. The second sort of point here is, in practice, of course, getting lots of labels is actually, painful and expensive. But often unlabeled data is actually pretty free, right? I mean, you can imagine just, ideally we would just like to be able to learn a good vision system by just having the machine watch TV all day. So essentially there's almost unlimited amounts of it, and it's free. We don't really have to spend money. It's the annotations that cost money, not the data itself. And the final point is that even if in practice you're still probably going to have some labels around, but you need to think of the unsupervised learning component is sort of allowing you to sort of generalize away, create the systems that can generalize off just a few labels in a particular target domain that you care about, right? So if you really understand, or a model that just understands the structure of the data, you provide a few labels in a particular part of the domain space, you still should be able to do a good model. So this ties in to the whole sort of community of a whole enormous body of work on some things like transfer learning, zero-shot learning, one-shot learning, few-shot learning. Okay, so I'm not going to talk about this today, but I'm just making the point that if you have a really good unsupervised learning technique, it would feed into all of this. And then the final kind of motivator I just wanted to make is actually a sort of slightly interesting argument made by Jeff Hinton, and this is a sort of biological one, and he's arguing that essentially our brains have about 10 to 15 connections and synapses between the neurons, but we only live for about 10 to the 9 seconds. And so if we wanted to set those weights in some rational way, then we would need to be setting about 10 to the 6 bits per second, assuming you just have a kind of single bit per connection. And the point is that somehow when you're growing up, of course this is uniformly across your existence, but in practice, of course, you learn a lot more when you're an infant. But when you're an infant, your mother says to you, okay, this is a spoon. Occasionally, she doesn't say, this is a spoon, this is a spoon, this is a spoon, this is a knife, and so on and so on, every single second that you're in existence. So somehow, you do get some level of information, but it's really way sparse signal, and really dense signal that you would need to be able to sort of, learn according to this argument. And the only source of information that has that amount of information is really the signal itself. Okay, so that's sort of arguing why we have to be able to learn just from sort of, streams of the raw data and not necessarily relying on kind of these external labels. Okay, so I think it is worth saying, I think that, I think if you look at what most of the sort of, cutting edge groups work on deep learning are doing, most of them are actually working on unsupervised learning in some form or another. Okay, I mean, it feels like that's still a big unsolved real problem you don't know how to address. And actually, I did want to make a little aside here, just because I guess I'm old enough to have remember what it was like before things went crazy, you know, in around 2011, 2012. It's actually interesting to know that deep learning was all about unsupervised learning when Jeff Hinton and others kind of revived the whole thing in the mid-2000s. So in fact, there was a pretty cool paper by Jeff and one of his students, Russ Lunikoff, on restricted Boltzmann machines for doing unsupervised deep learning. And so that was the main focus actually for quite a few years. And then people realized that the plain old supervised methods just work really well. And so everybody's been going, you know, gangbusters on those for the last few years. But still somehow, you know, the original sort of inspiration and goal was to try and crack deep unsupervised learning. Okay, so just to try and talk about things and try to put some structure here. We're given some big data set X. And in the previous talk, we were considering for every example X, you would have a corresponding label Y. Okay? Now, in the unsupervised learning setup, you're not going to be given that. The simplest way of thinking about unsupervised learning is where you're just trying to build a model of that data distribution. Okay, so it could be that I put P of X, but it could be just an unnormalized probability distribution, so it just has some sort of unnormalized energy attached different points in space, but building some kind of density model of that data. Okay, now, so if we have that, what can we do? Well, we can do things like we can draw samples. Okay, so that's something that can be very useful. We have some way of computing a probability, or at least some maybe some unnormalized probability of some particular example that someone gives you. We would also let you do things like if you have some sort of in practice, you might want to think about building conditional density models. So if you have some sequence, maybe you want to have a distribution over the data samples at the current time step, given the previous ones you've seen in that particular example. And I will go through some models that using deep learning to tackle this problem. I think what's somewhat interesting about them is that it forces you, because you're trying to build a model over the space of X. In practice, forces you to sort of think about different architectures from the ones we were talking about previously. So previously, we were talking about models that were really trying to do high-level tasks, like classifying images or segmenting them, or if you're doing something like other domains like speech, you might be trying to recognize the utterance from the waveform. But if you're trying to sort of construct things back, so if you want to build a distribution over the input space, then you actually need to have some sort of architecture that's going to go the other way. So those require kind of slightly different architectures that we'll look at in due course. Okay, and then there was a sort of slight conceptual sort of twist, I suppose, some people call self-supervised learning, where the idea would be that you essentially can have some function y that you are able to in a sort of free way, extract from the input domain X. Okay, so that's in other words, the key point here, the distinction between this and the previous one is that somehow you want to use all the standard sort of architectures that work so well in the supervised case. So what you're going to do is contrive some way of constructing a label from each unlabeled example that you're given. Okay, so I'm just going to give you because this sounds a bit abstract and weird. Let me just give you an example. So for example, one great example of this is word to vec. Okay, so this is an example from the NLP domain. You're given some text, say a sentence like the cat sat on the mat, so that's your X. And that's the input thing. What you're going to do is you're going to basically, you're going to give as input to your model all the words in the sentence except, say, the center one, and you're going to try and predict the center word from the context. Okay, so this way, it's not like there's a human-provided label. You can construct the separation into X and Y, and automatically given this particular sentence. And this way, this is the principle by which word-to-vec operates, and it actually does end up learning a function that maps X to Y that works really, really well. Right? So it's something that it's able to, from this you can get very good embeddings for text. Now, what in practice people use, so first of all, there's two things to say here. So one is that first of all, constructing this Y often requires some kind of insight into the domain at hand. Okay, so this is in some sense, whereas by contrast, when we were talking about building these kinds of models, this is, in theory, could be completely agnostic. In practice, of course, the architectures you might use might be a little bit tuned to a particular domain to work well, but in this setup, humans have to inject kind of knowledge about what this particular Y should be here. Okay, so just to be clear what I'm writing here, the idea is that you have some example here, xi, you pass that through the neural net, it gives you some approximation to your label Y that you've extracted from just the input example itself. Okay, so this Y of xi would be like the word sat. And then this piece here would be a prediction as to what this center word would be, or something like that, a distribution over vocabulary. Hopefully you assign high probability to the word sat. So I think one of the reasons that people so in practice what people do is they will use this kind of self-supervision as a pre-training recipe for some subsequent task. Okay, so the idea is if you sort of pick this target Y in the right way, with all the functions, if you pick the Y in the right way, then the representation you would learn would subsequently be useful for some, some downstream task, which may not necessarily know what it is. So I think the key point here is that people just want to be able to reuse the standard architectures that work so well in supervised learning. And so we'll look at some examples of this in the vision domain. But I will come back and explain a bit why I think it is a little bit artificial, because you can think of course, if the Y was the identity function, then it would be very similar to what I was saying on the previous slide. Or you can imagine the conditional thing. This would only show the previous elements in the sequence, and then this thing would be the future element of the sequence. So it's a little bit of a artificial separation. Okay, so let's just talk about, I'm calling it density modeling, but you could call it just unsupervised learning. So I'll just talk about a little bit about the kind of building blocks that people use with deep net. So now I believe you had some lectures already about variational auto-encoders. So hopefully most of you, someone covered a variational auto-encoder today. Okay, yeah, all right. So, so the models we were looking at previously basically were just encoder only. Okay, so they were taking some input, pass it through, some convolution or whatever, some nonlinearity, and get some features. So in an autoencoder, you're going to have some way of going back from the features to the input. Okay, so it's going to produce some kind of estimate of the input, and then there will be some usually in the most basic form. You would need to have some sort of constraint on this model, otherwise it could collapse the sort of the identity function in both pieces, and so on. Okay, let me see. So in practice, yes, each of these blocks here is going to be like some sort of deep net, and we've got slightly different architectures for the decoder because it's not mapping from kind of image to class label or some high level features. It's mapping from features back to pixels. So you need to have slightly different bits of building blocks basically in the decoder. So one example of this was the variational auto-encoder. So this is one where you've got, and this is essentially gives you a sort of probabilistic interpretation of an auto-encoder. So that you would have you have a network that basically parameterizes this distribution. So given an x, it would output like a mean and a covariance over the latent variable z. You have some sort of prior z on the latent variables. So that's important because this thing's a sort of a true generative model. And so at test time, what you would do is, sorry, I'm getting ahead of myself, you would have then a decoder that would take the z and then decode back some distribution over the input space. So typically that's just isotropic Gaussian noise around a mean estimate, again reduced by a deep net. Okay, and so this objective function here is just some kind of reconstruction term. So you will want to assign, this thing will want to assign hyperability to the original input image, and then this term is just ensuring that the latent variables produced by the encoder are close to the prior z. So at test time, this is a generative model because you don't use the encoder anymore. You can just draw a sample from the prior, and you can push it back through the decoder, and hopefully you should get realistic samples from the domain. Sorry, I have a slide. There we go. Sorry. That's the cat. Okay, so that's another sort of huge family, and there's a whole lot of examples of this. We're going to look at one in a bit more depth in due course, which is a sort of variant of this that apply to video data. And then another sort of classic, you could think this isn't, truly speaking, a density model, but one very common approach that everyone is very excited about these days are things called generative adversarial networks. And so the idea is here that you basically have, instead it's called a generator rather than decoder, but something that will map from some fairly simple sort of isotropic noise vector down to image space, or whatever domain you care about particularly. And what's interesting about this one is it's got a slightly different, in these previous ones, you end up more or less with just a sort of L2 loss term between the reconstruction and the original input. In this one, you've got a slightly more fancy loss function, which is actually a classifier which is trying to discriminate whether it's a real example from the training data or it was a generated example. And these two things are set up in a kind of an adversarial way, where they play this kind of minimax game, where one's trying to fool the other. And it turns out, somewhat surprisingly, you can actually train these things to generate really good examples of quite complicated domain. Generate like pretty high resolution images, or you can generate molecules and stuff like that if you have the appropriate generators. So I'm hoping Sebastian, in his lectures, he said he was going to talk about GANs in the schedule, so hopefully he'll talk a bit more about this. Okay. Yeah, sorry, my slides are totally wacky. So anyway, yeah, bottom line is, just to zoom in a little bit, what would happen, you would, in most of these generative models, which are deep, you would be sort of drawing a sample from the prior, and that would be a prior over your high-level features, which hopefully are sort of easier to model with some simple prior than you would have from, say, the original input space or low-level features. And then for each layer, you would sort of decode. The decoder would be something, again, like some sort of convolution. And then you have some of them have sort of unpooling operations, which are kind of a little bit like just averaging out, placing the element in pooling you have a sub-window which you take the max or average, and in unpooling you sort of put a single element down, either at a random location, or you could just put the average value, the same value, just copy it from multiple locations. And then they typically do have values in also as well on the way down. Okay? So then you can do this multiple times, and then that gives you an example. Sorry, my animations are all wiped out. Sorry. Okay. If you want to do something like conditional generation, how would that work? Well, typically what would happen is you would, your previous information will be passed through some kind of encoder. So that's your, if you think about video here, for example, that would be your convnet. You'll get some high-level features, and then you would, the top there, or whatever this thing would in practice be kind of a predictor that's trying to like predict the next level features. And if you wanted this to be a truly kind of, stochastic model, you would maybe have some sort of prior distribution, which would would add in some sort of, you would have some distribution of the high-level features, which you would add noise. In practice would be sort of adding noise or whatever. You came out the top of that encoder, and then you would push down through some decoder to generate, say, the next frame. So we'll look at a specific example of that later. Right, so just to talk about a little bit about what will happen. So if you've trained these kinds of, sorry, let me just run back through. So if you train these, oh, my slides are out of order. Oops. Sorry, I'm just going to skip to the next one and then. So, so there are various twists on this. So what I was showing previously was where you would somehow have two objective terms, one maybe on the high-level features, some sort of prior to stop them collapsing to some silly thing, and then you have some sort of reconstruction constraint. There are types of deep autoencoder where you actually have reconstruction terms kind of into the intermediate levels. So you would actually have a reconstruction term between these, the features that this thing produces and what this thing decodes here. You have some sort of L2 loss or something at each of the levels. And this is something called a ladder network, which is kind of a pretty interesting kind of unsupervised deep autoencoder unsupervised learning approach. Some of the early deep learning models were actually had this kind of form flavor where you had things like something called they would take these things called Boltzmann machines, which were they were autoencoders but of a particular type, often when you had binary features. And these things would be stacked up and train these things layer-wise. So they would have a sort of flavor a little bit like this. So the idea is often in these kinds of frameworks, you're independent of whether you actually have a loss function between the features here or not, you would have this sort of, you basically have an encoder and a decoder that you could used to train in some unsupervised way. And then what you can do is, this is my previous slide, sorry, is what you would do is you would take the, if you want to do sort of fine-tune on the target task, so you had a few labels available to you, you could then basically, take your frames and pass them through to make some prediction about the label, and then compare that to the ground truth, and then you get some error, sorry, the animation's all messed up. You get some sort of backprop signal, error signal to backprop through refine. The bottom line is you would train the encoder by using some sort of unsupervised learning framework like a Variational Auto-Encoder, but then you can fine-tune the encoder for a particular task at hand. So you would then just pass the input in, push it through, and you would be able to predict labels for you. Okay, sorry, slightly ahead of order there. Okay, yeah, there's actually a whole ton of these things, and it's just impossible to kind of cover all of them. I mean, there's denoising autoencoders, there's various types of, there's sparse coding with some sort of feed-forward encoder, some Yann-Kuhnmetz models on that. There's all this switch-box machine stuff that I think people don't work on quite so much these days. And then you can also, there's also the GANs, for example, of like something you only have a decoder, there's no kind of encoder, at least in the basic variants. So there's a bunch of sort of things there on sparse coding, and there are other types of decoder models like sparse coding and so on. So just to look at a bunch of, I thought it'd be just worth looking at a few papers. So this is a simple example of a sort of conditional generative model for images. Okay, so this is one where you're going to generate pixels one by one in sort of raster scan order. So the idea is you want to generate that pixel, you'll condition on a little neighborhood. You might do that over scale as well. And so you can see that your overall probability distribution over an image, the bold X, is going to be a product of these conditionals, right? We're predicting pixel I given all the previous ones, which means the ones sort of up into the top left. And you might say, well, it seems like a slightly slow approach to doing it, but it does have some advantages. So often it's very difficult to kind of construct or to parameterize distributions over sort of very high-dimensional things like entire images. But if you have to parameterize just over a single variable, like a single pixel, then you can do things like have a discrete distribution, which makes things a lot easier. And that lets you also have things like multimodal distributions and stuff like that. Of course, I mean, you could have if you have a continuous distribution over a high-dimensional space, you could have just a single Gaussian blob. But it's not very helpful because you don't capture any multimodal stuff there. So the idea is, when you're generating, you would just draw a sample from this discrete distribution, stick that pixel down, and move on to the next one. And then the next generation would, of course, be conditional whatever sample you drew there. Okay. So this was, I think, quite an interesting work from a couple of years ago. And there's a bunch of they extend it to video, this is some work with DeepMind folks, and then there's a bunch of other kind of related sort of density estimated techniques that use deep learning and stuff like that. So one that actually I think has had a lot of practical application, this is pretty cool, is something called WaveNet. This is the same, so broadly the same idea, they're going to generate in this sort of conditional fashion. They use this for speech. So there's these are sort of different little windows from the speech waveform. And what they have here is a deep net with multiple hidden layers. And they're using sort of a type of convolution that naturally, they're not doing pooling, they're doing a type of convolution which is strided, if you notice. So they have, say every two time steps they look at, rather than looking at every single one. And then the same thing is repeated at sort of the higher layers. So the ultimate point is that an activation up here actually depends on a whole bunch of, it depends on a big time window of the input. Okay, so this way they can actually, this way they can actually have, the final, what they do is end up generating a new sample here, which they then copy. The animation reset. Okay, so it goes here, and then they copy that one down to act as the next piece of input that then will then condition on for the next time step. So the bottom line is that each sample they generate up here will depend on kind of the large input time window. And again, they do this because they're generating kind of things one by one. they can use this discrete output distribution. So they really can capture kind of, each sample that can be multimodal. So they're drawing from multimodal distribution, they draw each sample, so that really does let them capture kind of pretty complicated distributions over the full speech waveform, X. And so this is actually, Google's got these amazing results on generating very, very realistic human speech from this, and they've been using this in some of their sort of digital assistants and things like that. So this is, I think, a pretty nice success story for an unsupervised method actually being used in practice for some real application. Okay, so I think in general these models that try to predict sort of the future time steps are actually pretty important. And I'm going to have a slight detour as to just to talk about some of the more general problem of how you build an intelligent robot or an intelligent system in general. So what we've been talking about a lot in the the first part of today was really this perception part, how you take the world and try to get some kind of understanding about what's going on from the raw sensory data. But you also, if you kind of build an intelligent system, you've got to figure out how to act as well. And this is, again, it's a kind of loop, right? These are all very old ideas, many people have pointed out. Okay, and so in some sense, if you want to actually do a good job of taking smart actions that maximize some kind of reward in the environment, you need to plan which actions to take. Okay, and so to do that effectively, you do have to have some kind of model of the world in your head, or the robot's brains, to figure out what sequence of actions should I take. If I took this sequence of actions, what would happen to if I'm trying to pick up this glass on the table, if I take this particular sequence of actions, will it actually pick it up or not? Okay, and you want to be able to do that, of course, without actually doing anything yet, just sort of imagining it. So in practice, what you want is some sort of system like this, where you have some sort of perception, and then you have some sort of world simulator that is able to sort of say, well, if I took a particular action, then my world state would advance to this, and then I can use some sort of, some reinforcement thing saying, well, is this a good state to be in, and so on. And then you can sort of roll this out through time. So you'll see that this is basically a predicted model of the world. Given my previous sequences and some now new action I take, what would be my future time step? So in other words, the key part of this whole framework to be able to sort of plan effectively, sorry, I skipped that. To do the planning, what you would do then, of course, is try and work out at the end of this, am I in a state that I think is good, and how would I adjust the actions to sort of basically take to find a good state. But the key part of this, which is hard, is really coming up with a kind of accurate simulator of the world. Not just in some little toy robot simulation, but in actual really complicated environments. Yeah. Well, this is just a very abstract thing. So this is a generic. This is like a robot in the world trying to achieve some task. Like maybe you want the robot to build your sort of IKEA furniture or something like that. Yeah. From what's there? Well, that probably isn't essentially. This is an incredibly high-level point I'm making. Okay, so any model-based RL system is basically doing this. Okay, so I'm just trying to emphasize why, in practice, most model-based RL things are operating in kind of somewhat idealized state spaces or something like that. And the hard part is just trying to create ones that actually work, in a just arbitrary, noisy real world setting. Okay, so just to give you an example here, so this is just a little toy paper I was involved with where we, had some, in a simulator, had some wooden blocks, and we put them in some random configuration, and you try to predict what would happen in the future. Okay, so you can see that, sometimes they would fall over, and they would land, like this, and you can train the deep net to sort of, give the initial image, make predictions as to the future locations of the blocks. Okay, so that's just, supervised, purely supervised training there, because you can generate the future in the simulator and then just try and copy the deep net. Okay, so ideally you would want something like this that you can learn without having to sort of have a simulator and sort of simulate everything. You'd like to be able to sort of learn such a model just by watching a video or something like that. Okay, now the other thing which is actually worth pointing out here, and this is something which is an important point, which I was sort of alluding to earlier with unsupervised, with sort of these predictive models, or this world simulator, which is what I'm calling it, is the aspect of uncertainty. So you can see here that in this model, which was a very simple one, it was really smearing out. It wasn't sure where this yellow block was going to go, right? So it starts getting all uncertain and smearing out the pixels. Of course, in practice, there are multiple possible features, sure, but each one should be like a crisp, block just in a slightly different location. So this handling sort of uncertainty in the future is sort of a crucial part of. So you're not going to be able to do this purely deterministically. So there's a lot of work on sort of. Hold on. Slightly. Before I get to the uncertainty part, let me just iterate. So I'm going to talk for a little bit about video prediction. So this is in some sense trying to build like a world simulator, you can think about it, or predictive model of video frames, just by watching video, right? There's no human labels and annotations. So it's really just predict frame xt plus 1 from all the other ones. And there's a lot of people who have been working on this recently. People just, brute forcing it with LSTMs. You can try things where you make label variables discrete. That's actually there's another recent DeepMind paper I've got put in here, which is really cool doing that. You can try using optical flow, kind of predict that, and use that to update the current frame. If you have actions available, which you would do in a real robotic setting, that's obviously going to be helpful to make predictions and so on. So this is actually just little clips from some paper that Jan is involved with. So when it's red, these are generated. So this is just, you can see they're conditioning on the certain set of frames and trying to predict what the future ones will look like. Okay, so they're quite very, very short-range predictions, but they are at least doing a reasonable job on kind of seeds. Okay, so just to get back to that prediction point I was trying to make earlier. So there's just inherent noise and uncertainty in the world, right? So there will be many possible futures that are all reasonably plausible. And you've got to have a loss function. You need some way, basically, of handling this in the model. And if you just do a simple, if you treat your model's prediction as a point estimate, and then just have a loss function that just penalizes that with respect to the ground truth, your model can make some plausible estimate of the future that just happened to be kind of slightly wrong because, there was, the model didn't, had the block in slightly wrong location when it started or something like that. So, in other words, if you just have these very simple sort of, L2 error between prediction and the ground truth, you end up with blowing things out. And that's what we saw in that previous little thing here, okay? So, to do it properly, and this I think is quite an important aspect of supervised learning, there's two sort of broad ways of doing this. So one is to use GANs. So GANs are a way of you have a loss function between distributions now, not point estimates. And so that little clip I showed you was actually from this paper, which is indeed use GANs instead of just an L2 reconstruction. And the other way of doing it is you have some sort of explicit, some kind of latent variable in your model which counts for uncertainties. The idea is a different version, as you change the latent variables to different values, each one of them would encode like a different future in some sense, right? So if you just sample the latent variables, that's like sampling a different possible future outcome additional in previous frames. So what I'm going to do is just talk through one particular piece of work that one of my students, Emily Denton, was involved with, that does video prediction using sort of a latent variable approach. Okay, so this is just, so the basic idea is you're going to have, this is actually, you can think of this as a variational auto-encoder. The basic idea is you're going to have an encoder which is ingesting the previous frames. You can think of this as like a little, it's taking the previous frame, encoding into some high-level feature space, and then you've got a little LSTM in here which is sort of recording in some sense all these features from the previous frames, and then it's going to decode out to some prediction as the future frame. And then, so in some sense, this is purely deterministic, this pathway. Okay? So in some sense, if you didn't have this piece in here for a second, this would be just a purely deterministic prediction about the future given the previous frames. Now, of course, what's going to happen is that there will be sort of random stuff that happens. Okay, so and so the randomness is going to be kind of baked into this latent variable z here, which is going to be sampled from some distribution at each time step. Okay, and then the idea is that you're going to take this sort of deterministically computed feature, this set of latent variables here, z, concatenate them, and then pass them through to decode. So the point is, like, if you draw different samples from this distribution, you will get different future frame generations. We'll look at some in just a second. And the key point is, this prior, at least in this work, and I'm going to contrast it with some other recent work, is actually learned as part of training. So you're going to learn a distribution of these latent variables, and that distribution is basically going to depend on the previous frames. So the previous frames, you've seen a certain amount of stuff, and say you've seen a ball. Say you throw a ball. It's a video of a ball being thrown. The ball is about to hit the ground, and then based on some because you've seen lots of balls being thrown, because at training time you have lots of videos of balls being thrown, you've learned a prior which would accurately predict sort of what the sort of likely uncertainty was when the ball hits the ground, and then it's going to bounce off potentially different angles. So let me just skip through this. So basically, yeah, you can think of this as a variational autoencoder. So this is if you just forget this piece here for a second, this whole thing is a big variational autoencoder. Oops, so the formatting's gone wacky. So the idea is that this would be at training time, you present a true frame, future frame, encode it to some distribution, and then you would draw a sample from it, just like you do in your variational autoencoder, and then you would use that. This is then your decoder piece here, which would then decode back to your pixel space. So test time, so training time, you have this available, which is a model which sees the true. So yeah, you have then. So training time, you have this frame available, and then you would just have a simple L2 reconstruction. Now you could replace this with a GAN loss or something like that if you wanted as well. It's a bit superfluous because the sort of the uncertainty is kind of meant to be captured in this latent variable Z. And then there's also a term here to sort of train the prior. So we use this inference model to train. There's another similar framework here, which is basically learning a sort of distribution here, which is going to be close to the ones you've got. So the key point is that in this prior only gets to see the previous frames, whereas this one, you only have this piece of training time, gets to see the latest frame, xt. Yeah, so that's right, that's the major importance from these two boxes. Right, and so what happens, right, you will take your previous, you generate a frame that gets put back into the prior, that gives you a new distribution, you sample from it, and then you take, again, the generative frame also gets put in place in here, in the encoder, and then you decode to a new frame. And you just keep repeating that until you make the time steps. Okay, so just talk a little bit about these things. So it turns out that when you're doing this kind of stuff, it does, the structure of these priors and how you use them really makes a big difference. So it turns out there's some sort of concurrent work with ours where they were doing something very similar. So this was their approach, this was ours, and in their case they're also conditioning, they're building an encoder. It's conditioned on the previous sequence of frames, and just so that's the training time, and they construct the thing. But when they generate, they actually just use like an isotropic prior, which just have no structure to it, sampling that at each time step. Okay, and so I guess the major sort of difference is in our approach, the prior we're sampling from does actually depend on the previous frames in the sequence. So there's a lot more sort of richness to the prior distribution you're using. Okay, so just to show you, these are little, so what we're seeing here is like ground truth videos of pairs of digits bouncing around. When they hit the sides of the frame, they bounce off a random angle, so things are inherently kind of uncertain. These are just showing the kind of generations that you can get. So these last three columns, the last three in each row are actual samples from the model. Okay, so you can see we're able to sample here. These things very, very toy setting, reasonably, the digits stay crisp, and then the few different samples all look, you have different motions being generated. So each one of these corresponds to a different random variable you've sampled, and you just put into the encoder. And in these models, you can actually also, when the collisions are going to happen because you generate the data, so you can look at that prior distribution, which depends on the previous frames, and that prior distribution will vary, its variance will change. So it's making a prediction, essentially, as to when it thinks uncertain things will happen. And you can see, indeed, that the uncertainty, which is this blue curve of the learned model, does vary as a function. It coincides with the collision points when the digits hit the wall. Okay, so when when the digits hit the wall, as I said, you get a bounce off randomly. That's the way the data is generated. And you can see in some sense the variance here spikes those instances. So the model in some sense knows when things are behaving fairly deterministically, and then it also knows when things are about to go crazy, and it's going to have to increase the variance if you're going to make a reasonable prediction. And this is another little visualization of the full distribution. So you have a digit that's coming into a wall like this, and about at some random angle. This is just showing the velocity distribution across many different examples. So initially it's just a delta function, because it's moving at a constant velocity towards the wall. And because for each example you're going about up in a direction, when you plot the distribution, the histograms that go over many, many different generations, this is the ground truth distribution. You can see it becomes almost uniform. And then as you have subsequent collisions, that gets clipped. And then over time it shapes up into something quite complicated distribution. This is shown, you can actually capture these pretty complicated distributions of features reasonably well with these kinds of models, right? So this is a delta function, and again, you can see it getting shaped. It's not exactly the same as the ground truth distribution. It's not, it's still getting it roughly right, even quite a long way into the future. And when you try these things out on real images, this is a data set of sort of a robot arm just nudging objects around on a table. And these are just, so this is just the ground truth examples here. You can try to basically, so you can, if you just come back to that planning example I was referring to, if you have a good predictive model of what will happen when I move the arm, when you move the arm in a certain way, that will then let you plan how you might want to say, pick up a certain object or nudge it to the front of the table or something like that. Now, to do that, you have to have a good predictive model as to what's going to happen, what the future state will be if the arm takes a certain action. Right? So just to be clear, it's not, in a lot of robotics things, they just think about the state of the arm, and I'm worrying about how the arm will interact with the complicated set of objects actually on the table. So when you try these things, so this is the ground truth here, and these are sort of, you can look at these ones here, for example, these are just like different samples from the thing. You can see in some of these are like the pincers are opening and closing on the arm itself. So these are all just completely generated. When they're in red, they're completely generated frames. And you can see this is going out quite a long way, and it's still remaining reasonably sharp. To some extent, when this thing nudges, when it nudges objects, you can see the objects sort of move. They're not like explicitly alike. But the idea is, so this is obviously just one piece of the overall planning framework. Hopefully you could integrate these kinds of things into an actual, an actual robot planning system. And it's just, some of this work's coming out of like Peter Beale's group, the Secular Beans group at Berkeley, and they are trying to do these things. So this is the one where the prior is much simpler, where you're just simply sampling from this sort of classic Variational Auto-Encoder prior, which is just unit variance zero. And you can see very quickly the reconstructions kind of go to hell. And then very good. Okay, let's see what was that. So let's move on to some of the self-supervised learning stuff. So I think in the previous stuff I was showing you there was an effort to sort of predict, future predicting back to the input domain, right? Kind of predict sort of pixels. In a lot of the ways people use this, the unsupervised learning is really as a kind of pre-training phase for some sort of high-level task, like classification or detection. Okay, and the idea is here, you really want an architecture that's going to be really good for classification or detection. You need some way of sort of initializing it in a smart way, not just using sort of random weight initialization. Okay, and so this is just going back to what I was saying earlier. The idea is to try and come up with some sort of signal that you could derive from the input that might help you do this. So in the vision, there's been a bunch of works, basically, particularly in the vision space, which have tried to do this. I think in the text space, it worked today, because I gave the previous example, works very well. In the vision space, things haven't worked quite as well. People are trying this whole thing. So there's a whole bunch which just use images, which I'm going to go through in just a second. There's a bunch that use videos. There's some sort of multimodal type things, and people have actually started trying to do it with also actions and stuff like that. So I'm not going to go into all of these, but I'm just going to take a few examples. So one really simple one is actually trying to just colorize images. You might think that's a weird way to try and do this. The basic idea would be you assume you're given a color image with the input to the model, which is going to be a standard ConvNet. There's no kind of fancy autoencoder or anything like this here.
is going to be just the luminance. Okay, so you just give the grayscale image to the network as input, and then the target is going to be the two chromaticity channels, A and B, because this is LAB color space. Okay. Now you can get this. So just to be clear, right? This is Y you can get for free, assuming your image is a color in the first place. And the idea is then your loss function is going to be you're going to combine your input luminance with the two chromaticity channels. Sorry, back a second. So yeah, you use a DNet to predict from a luminance the two chromaticity. You'll combine them with the original luminance to get a color image, and then that gives you some sort of loss function now that you can compute back compared to the original image, just using like an L2 pixel space. Error or something like that. Okay? And then you can say, you can just try and backprop any error through this network. So again, this is just a standard CompNet. There's no standard, you think of just like, from those auto-encoder models I was talking about before, this is just an encoder. There's no decoder piece back to the original input space. And then you might say, well, how on earth is this going to do anything? Well, if you think about it carefully though, you have to have some sort of semantic understanding of what the hell this is a fish in order to know where to put the colors, right? I mean, it's unlikely to be, say, pink or something like that, right? I mean, fish tend to be yellow or some blue color or something like that, but images they underwater. And so this is actually kind of a pretty, amazingly actually, it's quite a powerful way of doing it. It's incredibly simple, very easy to do, and so on. Yeah. So I realize I slightly misspoke here, because this isn't completely a standard CompNet, because there is a piece where it has to kind of map out to pixels. So it's even though it's not like a separate decoder exactly, but there is I skipped over at the end of the last lecture, but there are some architectures that will sort of be good at reconstructing pixels that they use for this. So what I'm going to do is I'm not going to go through the results, show you results for all these each time. I'm going to share a bunch of these, and then at the end we'll come to some sort of results table where I'll describe how all these things work. So this was the other thing that people know, as I said before, the whole works of VEC idea is pretty neat. So this is actually just flipping it the other way around to kind of predict the context from the center word. Word to VEC have both incarnations in. So what's the visual equivalent to this? Well, you can imagine taking like patches from an image that you're not from different random locations. So you randomly pick one of these locations and take a patch. Random locations around the center patch. Pick one. Sorry, this is a crazy animation. Okay, maybe we use this image instead. Okay, there's your random sample patch. You sort of try to bias it so it tends to be on an object. So they have a way of doing that. Then you randomly pick a second patch from surrounding that one. You have to leave a little bit of a gap, so you can't just cheat and copy the edge, use the edge information to give it away. And you randomly pick a location. My slides will work again. And then what's going to happen is you're going to pass these things through your favorite CompNet, and this network is really just going to try and predict a discrete label, which is which one of the 8 positions are you in. Okay? So the idea is that if you understand the semantics of objects, you should be able to solve this problem. Okay? You can just figure out the relative positions of these two pairs of patches. And then people, there's other papers which take this to a kind of extreme. They just give you a crazy assembly of patches. You could, like a jigsaw puzzle basically. And the idea is what they're going to do is just, take a configuration of the jigsaw pieces and hash it into a table. And so now you end up with this very big hash table of all the different possible, arrangements you could have of the jigsaw pieces. And then you just have a big network which takes each patch in turn. There's shared weights. This is a CompNet here. And then the softmax now is basically over the hash table indices. So, so each, if you output 64, for example, you're basically, the network's saying, I think, the arrangement of patches is in the following, right? So this would be, put patch, the top left one with patch 9, this patch here with patch 4, patch 6, and so on. So again, to do this properly, you have to understand the semantics of the object. Okay,
Now, so before I realize that the results table is going to be a few slides away, the whole purpose of these approaches is to try and, is pre-training for some kind of semantic task. So the idea is that all these things, of course, you've picked this sort of particular setup such that it's going to induce you to learn in a sort of free way some semantics about visual objects. So of course, if you didn't care about doing classification ultimately, maybe the representations you would learn here sort of automatically wouldn't be actually much use. So that is a sort of important thing to keep in mind, right? To actually, people are picking these tasks carefully in a way that is sort of designed for a particular purpose, and that's for sort of doing subsequent sort of high-level semantic stuff downstream. So there's another thing, this is another one where people actually are trying to, you could say, well, why don't you try and predict sort of, just pixels in the center of the frame or something like that. So that's another thing someone did. You can actually try, you chop out a patch of pixels, you take this thing, you shove it through the network, it tries to predict what's missing, and then you just can compare somehow to the ground truth patch of pixels in the middle. And this thing, if you try L2, you get very blurry answers. You can try an adversarial thing, which looks kind of wacky, and then they have some sort of combined loss function which combines the two to give some sort of reasonable answer. This is another example. So actually, I put this one in the self-supervised learning thing. But you could, you can think of this as a conditional, another conditional model. It was conditional outside the intermediate side. Right, so and then moving on a little bit, so you've got things like videos. So you can imagine, so you can imagine everything I've talked about so far is sort of static images. In practice, of course, everything in the self-supervised learning part is to do with static images. With videos, you do actually get a lot of very rich information, and this. One particular idea would be, well, look, you actually see the same object in a bunch of different views. Maybe if you were able to sort of track the object reasonably, that would give you kind of, a very rich training set in which to learn about sort of, viewpoint invariance and things like that, images. So this work is about basically using kind of object tracking, so off-the-shelf object tracking approaches to track patches through videos, and then what you end up with is you take sort of the first patch and the last patch, and they form a pair. And what you would like to do is they end up using a ranking loss, where they will represent triplets. They will have a query patch, which might be, say, the first one in that sequence. And then they would present two other patches, right? One of them would come from the end of the sequence, say, this one there. And then they would have that's the sort of the positive example, and then they would have the negative example, which would just be a patch drawn random from another video or something like that. And the idea is that the deep net, which again it's going to be pure sort of classification type architecture, is going to go from these pixels to some kind, it has to rank this guy above that one. So it has to say which, hopefully it should prefer, this is the patch at the end of the sequence to some sort of completely random patch. And so what you're going to do, if you train this kind of loss, what it's going to do is learn a representation in the complement, which is going to basically understand this byte here is basically the same object as this one here. Right? So this is kind of cute because you learn all these sort of invariances about the object and about the domain and everything like that. Right, so the caveat is that you are still sort of using kind of off-the-shelf tracking machinery. Right? So that's still, some extra, it's free in the sense you don't have to pay a person to track the videos. So what they do is they basically took a bunch of patches from the YouTube videos with off-the-shelf trackers. These are the kind of patches of pairs that they end up with, right? So because they actually look pretty different, and then it ends up learning a pretty good representation. So just to look at, for this particular one, and we'll do a big comparison in a moment, where this gets you. So if you just train, so just to understand what's happening here, the paradigm is you're going to pre-train your architecture either using ImageNet or using this kind of feature tracking, or you're not going to pre-train at all and just do random initialization. Okay, so you're going to do that, and then the second stage, you're going to fine-tune using the training set from this data set, which is actually fairly small. It's a fairly small training set. So if you don't do any pre-training, then you're basically going to sort of end up overfitting that small training set. And so your validation error, which I think is what we're plotting here, is going to be pretty, the variation accuracy rather is going to be fairly low. And all these models are in the same architecture. Now, obviously, if you use the whole of ImageNet, that's a bunch of human labels. So you would expect to get pretty good representation, given that this task here is basically almost the same as the ImageNet. You're trying to do sort of detection and classification of natural images. So the ImageNet task and this Pascal task are almost the same as one another. So if you do that, you do actually do pretty well, right? As a precision. But the key point is about these self-supervised approaches is that, if you use, in this case, it was the tracking example, you actually do get, a big boost over not doing any pre-training, and it's not that far off the, in some sense, the cheating version of pre-training where you actually had human labels. The idea is that this was sort of no human labels, this was with human labels. So, the ultimate objective, of course, would be to get up to this level without any human sort of expert annotation or anything like that. That layout approach, that was the jigsaw thing I was showing you. I think that's what this bar chart's showing here. So there's this general sort of, the vision folks, I guess, at the moment are quite, this whole little industry going, trying to come up with these different kind of self-supervised learning approaches, which are trying to sort of, get up to this kind of, get up to the full ImageNet pre-training performance, but in a way that doesn't involve any kind of human, annotation or anything like that. Okay, so just I'll show you a few more. So this is just with video. The other thing you can do is videos clearly have temporal structure. So you can, this is someone pitching a baseball, or that's what they're doing, and you can clearly see that if you understand the action, then you understand there's certain ordering that should happen here in the way they're moving their arms and their legs. Okay? And so you can imagine this sort of little game that you can do here. You can take videos and you could generate sort of, you could shuffle the frames randomly. And so this is a little sequence here where the frames have been placed out of order in this column. Right, so look at this weightlifting example, right? So he person's about to pick up the weights, it's over their head, and then suddenly it's down low again. Okay, and whereas you have positive examples where things are kind of all nicely in order or something like that. And then what you would ask the network to do, of course, is to try and, discriminate the positive triples from the negative ones. Okay, so this is the kind of framework we do. So they put these 3 frames in, each one, because these are all tied weights, they're all the same weights for each frame. And then the network at the top, you have a classifier which just says, is this a correct, the correct ordering, or is this the incorrect ordering? So that's again something that's also free to kind of get that information. So this is now looking at a fine-tuning on, instead of image recognition, this is video action recognition. So this is one of the big data sets in vision. So if you have a random initialization, then as you try to train your big complement using random weights on this data set, which is very small, you don't get that high accuracy. If you pre-train an ImageNet, you get a very good accuracy, but of course you use human labels to do it. If you try this kind of shuffling idea of the frames as a sort of pre-training or self-supervised pre-training, then you end up, in between somewhere. It does certainly significantly better than just doing random initialization. And then just quickly, there's some approaches that in practice you often have videos that have sound, so you can imagine having image information with audio. And the basic idea is if you try to create a network that would go from the image to predict the sound, you have to sort of understand a bit about the scene, right? If the sound is that of a car driving, you'd have to know that this was a sort of separate object and the cars made certain sounds and stuff like that. So it basically requires you to have some sort of semantic understanding of the scene in order to be able to predict the audio from the image. So this is sort of, they have some network that does just this. They have some sort of audio representation they're trying to predict. They have basically big component outputs in this audio feature space. And then when they visualize what the network learns, this is an alternate visualization from what I was showing you in the previous lecture, you'll discover that there are units that they discover in the network which really look at, do seem to be localizing on people's faces, which makes sense because, a lot of videos have people talking, and stuff like that, right? So the network is able to learn the correspondence between when there's a person moving their head or their mouth, probably that, the sound that you hear on the audio is probably coming from, that object you can see in the person's face. And when they visualize on other examples, I guess they find people a lot, and then they also find, hear like waterfalls, it's kind of fun, so they can see the sound seems to be coming from the bottom bit of the water lands, or the waves that they put on the beaches. So these are all features that have been learned basically automatically by sort of regressing from pixels to audio. How much time do I have? 10 minutes. All right. Okay, so now the big issue I think is this, is that somehow when people say they want to solve the unsupervised learning problem, what they really mean is you want some sort of generic approach, right? It's just, whatever setting you're in, say someone gives you a pile of genomic data, you don't know what to do, what to label, or anything like that. You'd like to be able to learn, there's clearly structure there, you'd like to be able to learn it. You want some sort of method that doesn't rely upon having a smart insight about the domain in question that lets you select, the particular thing you want to predict, right? So this is the thing I was alluding to earlier, where Y extracts from you kind of the target signal that you're going to present as a target for your DNet from the input that you receive, or the input signal. I think there are one or two approaches out there which do have this self-supervised flavor, but are definitely domain agnostic. So I think I'm just going to use the remaining time to kind of go over those a little bit. So one interesting approach which came out a while ago, which I think is quite neat. It doesn't work very well, but I think it's quite thought-provoking, is just take, someone gives you a pile of data. Now what you're going to do is you're going to pretend that each sample in that data set is actually its own class. Okay, so we're talking about images here, but this technique in theory could apply to anything. So for example, if someone gives you a collection of images, even if there are 2 motorbikes in that data, each one of them will be treated as a separate class. And what you're going to do is to sort of perturb each example to make it into its own little mini data set. Okay? So this is the original one here. In this case, admittedly it's true they're using, I suppose, some level of domain knowledge about the types of invariants you'd like to have. So you would say, okay, maybe the color can change, maybe the lighting can change, if I can rotate the image slightly and translate it. So you make these different copies of the original input. And then this whole group of images becomes like class numbered 1, right? And then this one up here, and then you try to discriminate between that and the images of all the other examples in your training set. So it's this weird setup where it's like trying to do classification, but there's no kind of semantic label. Each example kind of is its own thing. Okay? This thing actually works surprisingly well. Unfortunately, it doesn't really scale awfully well to practical things. It did sort of inspiration behind this next work, which I was going to talk about in a bit more depth. I think this is kind of a fun paper from some colleagues at Facebook, Piotr Boszczynski and Armand Choulin. So the basic idea here is, this again is applied to images, but you could apply it to many other domains too. There's nothing particularly special about it. The basic idea is you're going to learn to map images to sort of random noise on the unit sphere, which seems a very weird thing to do. Okay, so the idea is you have some sort of sphere. This is like hypersphere, and you're going to just draw random points on it. And you're going to. The idea is that each one of these images is going to get sort of assigned
to one of these targets. Okay, now obviously the question that you immediately ask is, well, which image goes to which target? Okay, so this is going to be controlled basically by some kind of assignment matrix, which we will learn as part of this whole process. Okay, so there's going to be a sort of simultaneous thing, two things that are learned, okay, in this whole framework. One is the assignment, so the noise is going to be fixed, by the way, so the points will be fixed on the unit sphere. We'll learn this assignment as part of the training. You'll also, of course, learn representations. The idea is, of course, this box has an enormous amount of flexibility, so it can map all kinds of stuff, so it can twist the original input space such that it maps onto, each point here would map to some point over there. But it's also somewhat smooth as well, right? So if you have two objects here, which are sort of very similar to one another, like two bands or something, it's going to be easier to sort of map them to 2 points which are close by on the unit sphere rather than being completely separate from one another. Okay, so this is sort of relying upon somehow, even though combinates are very powerful things, there's always some, the very powerful function, there is at least some smoothness to them. Okay. So before we just get there, let's just understand a little bit where it's coming from. So we've given a set of images. Again, this whole technique doesn't actually particularly rely on images, but it's easier to compare to other methods if we use images. And here's that loss function we looked at previously. So you'd like to have, you're going to present each image, pass it through that deep net with parameters theta, and you've got some sort of target label y. Now, if you take the most general setting here, you're not given the y's, so maybe you think, well, I can try and optimize over the y's as well. Okay, so that's why we have a minimization over the y's for each example. And so if we were to write this down in some sort of actual simple, say, L2 loss function, this is the kind of thing you can imagine. You would have some, for each image x, you would just minimize the distance between the features you compute from x and some target features y. You would just obviously minimize both quantities. As you can see, there's always a major problem with this, which is everything's going to collapse, right? And you can just make y do whatever it wants. You can't do anything interesting. And you can think about some sort of constraint that, the different y should sort of be come too close to one another and stuff like that. But it's in practice, I think, it's very difficult to do any kind of optimization that can go on. Okay, so their idea, as I was outlining before, is that you're going to basically have a set of points drawn randomly on the unit sphere. So this is obviously not just in 3D or whatever. This is going to be in some high dimensional space. And then what's going to happen is you're also going to your targets y are going to be some sort of permutation matrix. Sorry, assignment matrix P rather. That is binary. That's essentially for each data point is going to select a particular sort of element in C. Okay, so P is basically given, its job is to basically pick a single, this is what these constraints are here, pick a single point on that unit sphere. And so this is their objective function. So it's very similar to what we had before, it's just that now we've kind of factored that y into a piece that's fixed. Okay? And a piece that is going to have some kind of constraint on it. Basically, it's going to be kind of this binary sort of assignment matrix, P. And so, basically, what's going on is it's a pretty simple alternating optimization. You're going to sort of update the sort of your forward pass here. You take your input example, you pass it through your deep net to get some features out. Okay, and then, given those, you will minimize the assignment. You'll figure out the optimal assignments, and I'll talk about how that works in a second. And then, once you've got the optimal assignments, you can then go back and do an update of the parameters in your DNet. Okay, in the representation you're learning. Okay, and then you can this is what these two lines do. Okay, so the question is, you might say, well, how do you do this assignment? It turns out, if your parameters are fixed, so just to be clear, in this update, the parameters of your DNet are fixed, x is given to you, that's your input, c is fixed, that's the noise on the unit sphere, so the only thing you're trying to do here is
is to figure out the best P. It turns out, if you sort of do the math, the problem you've got to solve is this one. So we're trying to find a P that maximizes this trace of this matrix multiplication. And it turns out that there's actually sort of, it boils down to some sort of linear program which you can then solve with some, this Hungarian algorithm thing in some efficient way. So there's an efficient way to sort of compute that sensibly fast. So that's basically the algorithm. So again, just like before, what they're doing is they're going to sort of pre-train this whole thing using that setup, and then they're going to take the last layers and go and replace them and fine-tune on a particular task. And everyone, for whatever reason, people using this Pascal thing as the target task, just because it lets you compare to other things. Okay, so just we covered some of these. These are baseline things. So that was the temporal coherence one. That was the that's the tracking the patches. This was the jigsaw thing. This was predicting color. That was predicting the relative two patches relative position. This was solving the whole jigsaw with the hash table and so on. Okay, so these are all ones I went over very quickly. The same as the self-supervised. Then these are sort of in some sense pure unsupervised ones, like GANs, variational autoencoder. BiGANs is sort of variational autoencoder. Sorry, it's GAN with an encoder module in it. So this is just to be clear what we're looking at here. So again, this is if you pre-train on ImageNet labels, right? This is the sort of again, ImageNet is very, very close to this Pascal task. It's the same, classification problem. And then what they're doing is they're fine-tuning on Pascal, and this is whether they update just the top layers of the network or all the layers of the network. You can see it doesn't make a huge difference. And you can see you get pretty high accuracy. So this is 80% of and basically what you discover is that all these sort of self-supervised things basically do reasonably, but they're still some ways off. Okay, so you can see in fact that colorization one seems to do about as well as any of them. So that's getting about 65%. It's still about 15% off. So again, you get human annotations for this one, but none of these have any human annotation. Other than picking in a clever way at least for these ones, picking the self-supervision function, like polarization or tracking patches. Okay, so you can see we're about 15% off. If you try this sort of plain vanilla autoencoder, it does pretty badly. GANs, the features you get from GANs just aren't that great for these particular tasks. And the BiGAN was better, but it's still always up. And then the technique I was just talking about, this predicting noise, does actually about as well as any of these other ones. So in some sense, this is using kind of less domain-specific knowledge than these guys, right? You're not having to have some insight about the visual domain. All you're doing here is just kind of basically map your inputs to sort of learn an assignment of your input to noise in the latency feature space. Sure, yeah, of course. Yeah, I think that's right. So I think the whole point here is it's not really about sort of. So the point is you could use a more powerful model, then this number here would also go up too, right? So the idea is we're trying to see like, how close can I get to supervised pre-training using some sort of. Okay. Yeah. Oh, yeah. I think that's right. I think they're reasonably general. It doesn't particularly matter the architecture you use. I think you can still do it pretty well. None of these methods are particularly tied to any, particular content architecture. Some of them aren't fully using Alex actually, because this one has to reconstruct the color channels. So that one is sort of, it's like AlexNet, there's a sort of decoder piece that's attached to it, generates that to pixels. So I mean, they're not all, they're using roughly AlexNet, but not. No, it's a really good question. So I think it serves the purpose of at least creating some kind of mini benchmark where you can compare. I mean, one of the big challenges I think actually, so I should have made a slide on this, is actually evaluating generative models. So if you ever actually try to write a newspaper on GANs and stuff like that, you'll know there's this terrible problem that the GANs aren't technically a true generative model. I mean, you're not able to compute low likelihood and stuff like that, like all that data. So all you're left with is just like generative computed pictures, which is it's hard to get past the image reviewers sometimes, unless the pictures are really amazing. So I think the purpose of these sorts of setups is that it does give you some objective score. Now, of course, you could argue that this is more about kind of the compatibility between your sort of unsupervised pre-training task and the target task that you're tackling, rather than kind of the innate generative quality of your model. So it's a little bit. I mean, it's a little bit different it's a different task for sure, but it is one at least you can attach numbers to, basically. What's that? Oh yeah. That thing was absolutely kick-ass, because we are above this number, basically. So that's an interesting one, because the hashtag thing, of course, you go, well, the labels were kind of free because they were sort of just there anyway, so you didn't need to kind of wait too much of it. But I think there's a general principle here that you do somehow, some of the principles that are embodied in some of these approaches, like tracking patches and stuff like that, right? It's pretty clear that infants do this, right? Children can track objects, they're not just looking at single frames of things disconnected and stuff like that. So we think that quite a lot of the principles we're using to train ourselves when we're little, it's not exactly what we do, but some of these ideas in here would seem like it makes sense. So one quick thing you can do, and this is just the Wojciechowski and Julin paper. I mean, if you just do nearest neighbors in feature space of the features you're learning, I mean, it does seem to understand the semantics reasonably well. I mean, they all look like this actually. Everyone shows good pictures. Okay, so the reason I singled this paper out actually is because it's nice and simple, right? It's very simple thing. There's no really domain knowledge. It scales pretty well, and at the time it came out, it has pretty much state-of-the-art performance about these unsupervised things. There's actually a pretty cool paper from Auro Vinyas that I took on archive, I guess he's submitted next, which is a little bit in this. It's not doing the same thing as this, but it's sort of similar vein of trying to be sort of domain agnostic way of doing self-supervised learning. So anyway, just to summarize, and then happy to discuss things for a bit. So I think in many ways the power of deep learning is already about learning good representations, okay? And so that's what makes the difference. It's not that it's that much of a classifier. I mean, if you have really good features, you just need a linear classifier and you're done. And so, of course, in the supervised scenario, that's what you're really using the labels for, is to learn that good representation. And so it's all about, in some sense, there's a whole bunch of methods out there that are trying to, the challenge is to come up with sort of a loss function that lets you learn the right representation. Okay? And what's obviously a bit weird is you're sort of, if you don't know ahead of time what your target tasks are that you actually care about, then it's hard to know what representations you should learn. So a lot of these self-supervised ones are sort of slightly cheating because they're picking kind of loss functions that are biased towards these kind of, high-level semantic interpretation type tasks. And so inevitably, representations that they learn do quite well at those things when they fine-tune with them. But I mean, I think to really sort of ideally, you would want some sort of very domain agnostic approach to doing this. Okay, and so most of these approaches, apart from that last one presented, I think are sort of tied basically to domain. And ideally, they would be almost as good as supervised approaches. an interesting kind of area. Okay, so I'll stop there. I'm sorry, it's a bit of a whirlwind tour because it's just such an enormous area, this, and it's almost impossible to kind of summarize, in a neat way. But I'm sorry, I'm happy to answer questions. Sure. Well, okay, so let's just let's take one of these self-supervised ones, for example, right? So say it's like this one here where you're tracking patches through the sequence. So what you have to sort of understand is that, well, the signal I have is, for example, there's going to be the same object in the scene throughout the whole video, and that if I can track a patch, the tracking a patch is going to be sort of useful in some sense, right? But it's like, say I give you a new domain, like text, a story or something like that. What's the analogy of this in a story? It's not actually very clear. Right? I mean, you can say, well, okay, maybe you have a character that's in a story that's kind of constant throughout different chapters of the book or something, but it doesn't really have analogous meaning in another domain. So this is what I mean being a bit sort of, exploiting that domain knowledge, right? It's like human insight. Like, oh, yeah, probably, we're pretty good at tracking objects. Maybe if we could get these tracks automatically, that would be a good learning signal for the algorithm.
Go back 2 slides to the competition class, this class also.
Yeah.
It sounds to me like, I don't know, like variation of the code is better than regularization.
Yeah.
So if you use the dropouts,
yeah.
This doesn't give you the same thing, right?
Well, okay, so dropouts are unstructured in some sense. So you can think about this as a very structured form of dropout where you're going to drop out. Well, yeah, hold on, slightly different because dropout applies it applies in the hidden units of the network. And it's relying upon being random, so that you have this ensembling effect. So this one, actually, when I realized I went through, I realized this probably shouldn't be in this section. It should be back in this sort of, the earlier part of the talk where I was talking about sort of, conditional models. So it's more like you're conditioning on this piece and predicting that part. Yeah.
No, so my question is basically why people tend to hack the data to get some better prediction, why it can also work better on the models, regularizing better.
Oh, yeah, right. Well, I think so. Okay, so that's a good point. We just actually go back a second. So in an autoencoder in general, right, what you're referring to is like, you might say, well, why don't we just put some fancy, clever constraint up here? So I spend a lot of time doing this. So there's a lot of work which I didn't talk about today on, maybe you put some sparsity term up here, maybe you add noise, all these things, right? There's a whole bunch of things you can kind of do to these features that might induce kind of interesting stuff to be learned. I think the truth is, though, it's not, the models never work that well, actually. And I think it's, in practice, what's more interesting. The truth is just reconstructing like the next, the same frame back again. So, if all you're doing is trying to reconstruct the input frame, it's the same frame, it's not like a video prediction, you're just doing the same frame, then, the only thing that drives you to learn anything interesting is just regularization up top here. And if people haven't been able to come up with kind of, functions that induce like really powerful structure in these two, the encoder and decoder. And I think in practice what people have found is that trying to do something else, like trying to predict the next frame, or predict other pieces of the image or something like that, tends to be it's less prone to collapse in some sense, right? You can't collapse the identity function doing that. I mean, if you do the identity function, you just be copying the previous frame to the next one, or something like that. And clearly that gives you a non-zero error. Whereas if you do the identity function here, you do get 0 error. So the only way you can drive away from that is by putting some kind of regularizer on top there. There's a lot of work on doing this. But no one's, the models just don't actually work that well. I mean, if you take the features and then try to fine-tune the whole thing. If you do the autoencoder, then you try this fine-tuning business. Sorry, my slides all messed up. If you try this business, so these are features that say I do sparse coding at each level, because you put like an L1 constraint or something on the features, and then you build up stack methods and try to fine-tune the whole thing. It just worked really badly. I mean, people were trying this a lot around about 2010. Myself included.
Are there any other questions? If not, let's speaker again.